yesterday we learned how to draw Lewis structures, and some of those Lewis structures had all single covalent bonds, but some of them had double covalent bonds. And today we're going to do a little bit more of that, but with a twist. We're going to add polyatomic ions in and also talk about resonance structures. So thinking about polyatomic ions, they're really anything that ends in ate. So let's think about some polyatomic ions. There are acetate.
Oh, examples.
And carbonate. Now you're just making stuff up.
Yep.
Sulfate.
Sulfate. Chlorate. Anyway, we have all of these we have all of these polyatomic ions. So, again, talking about polyatomic ions, I want to remind you that if you have a polyatomic ion like sulfate, I told you that the sulfate polyatomic ion was kind of like a family in a minivan with the one sulfur and the 4 oxygens, and that minivan kind of takes on a force field, and you can't separate them. Well, it so happens that the bonds within the sulfate are covalent bonds, so we can draw Lewis structures for them. And we will use the same methods. The difference, one difference, is that you have to add or subtract electrons to accommodate the charge. Remember, ions are either atoms or groups of atoms that have gained or lost electrons. And then the finished structure will have a bracket around it. So I'll go through some examples. The first one is ammonium. And the process starts the same. So you need to count the valence electrons. Ammonia, or nitrogen, has, it's in group 15, so it has 5. I'm just going to draw the numbers down like this. Each hydrogen has 1, so it has 4. Now that gives me a total of 9 electrons. However, this is an ion and it has a +1 charge. That indicates that it has either lost an electron or gained an electron. And what has it done? If it is leaving Matterville more positive, it lost an electron. Okay? Remember in my Matterville analogy, we had positive fatty proton in the nucleus with enraged electron Elliott outside. If enraged electron Elliott leaves, it leaves behind a more positive Matterville. So if you have a plus charge, it means that you have lost 1 electron. So in my tally, I have to subtract that 1 electron to give a total of 8 electrons. So my starting number of valence electrons is 8. Now, the next step, same as before, draw a skeleton structure connecting all of the things with single covalent bonds, and then determining how many electrons I just used. Each of these dashes represents a shared pair of electrons. So I have 2, 4, 6, 8. I have used up all 8 of those electrons. So let's just figure out if, when chemical bonding occurs, atoms are rearranging so that their electron configurations look like the noble gases, so that they have 8 electrons in their outer shell. Nitrogen only has 5 to contribute, but it wants to have 8. So one way this can happen is if atoms share electrons with each other. So nitrogen does indeed have 8 electrons around it. Hydrogen, because it only has 1 electron to begin with, is stable with 2. So each hydrogen, this hydrogen is associated with 2 electrons. This hydrogen has 2. This has 2. So each hydrogen has 2. So the distribution and the way I have the electrons and the atoms connected works out. The last thing that you have to do with a polyatomic ion is put a bracket around it and put your charge on there. So I will go through sulfate. Again, we need to add up the valence electrons as the first step. Sulfur is in group 16 or group 6A, so it has 6. Oxygen is in the same group, and there are 4 of them, so we have 24 coming from the oxygen. Now this has a negative 2 charge. What does that mean for my electron tally? We have to add an extra 2 to our count. So we have 2 electrons coming from the fact that this is an ion with a negative 2 charge. It has gained a couple electrons along the way. So my total is 32 electrons. Again, creating a skeleton arrangement. Typically you have a center atom, and if you have one element, one atom of an element, and multiples of another, it is standard that this would go in the center and the other elements would be arranged like that. I have put all single bonds there. I have just used up 8 total electrons, which means I have 24 left. So since I have extra electrons left, I'm just going to start distributing them in pairs on these atoms out here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now in this particular case, it worked out nicely where the electrons that you had left was enough to give each element an octet, or 8 electrons surrounding it. And it's nice when that happens, because then you're done. It's not always going to happen though. I finished this by putting my bracket around and then adding the charge. Now, we're going to do nitrate. But before we learn about nitrate, I want to teach you about something called resonance structures. Because nitrate is an example of where this can occur. With resonance structures, some molecules and ions cannot be represented by just one Lewis structure. And the example is the nitrate from the previous example. So I'm going to go back to this nitrate, and I have some extra room over there now. And we'll just go through the same set of steps. Nitrogen in group 15, it has 5. Each oxygen has 6, so we have 18. We've got an extra 1 coming from that ionic charge. 23, 24 total electrons. So I'll just put that up here. Okay, I have a nitrogen with 3 oxygens attached, so putting nitrogen in the middle. I need to give myself a little bit of room here. So putting nitrogen in the middle and attaching 3 oxygens. I have just used up 6 electrons, which leaves 18 electrons. I'm going to put them on and start distributing them in pairs with the hope that I will have enough electrons to give each element an octet. If not, I need to deal with that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, I have all 24 electrons on this structure right now. But as you can see, the nitrogen does not have 8 electrons around it. So when this happens, the next step is to look at sharing more pairs of electrons. Maybe a double bond or even a triple bond, or maybe even multiple bonds. So what is not satisfied right now is the nitrogen. So I need to take something that is attached to the nitrogen and steal a pair of an unshared pair of electrons and bring that into a double bond. Now, which oxygen should I steal from? Do you think it matters? It doesn't matter. I'm just going to pick this one because it's closest to me. So this pair of electrons right here is going to go into that spot and no longer, it's going to become a shared pair of electrons. So see, now it's there, now it's there. Now this oxygen has 2, 4, 6, 8. This oxygen has 8, this oxygen has 8, nitrogen, 2, 4, 6, 8. So it's all good. The last final touch is to put that bracket around with the charge. Now, I'm going to leave this here. I'm going to bump to the next screen just to point something out, and then I'm going to come back. If you look on the bottom, it says when resonance structures are drawn, they are separated by double arrows. Okay? Well, I haven't even drawn any resonance structures. All I've done here I drew a Lewis structure for nitrate. And the fact is, you guys told me that I could have put this double bond anywhere. I could have put it there. I could have put it there. There are 3 variations here. To draw resonance structures, what we have to do is draw all 3. So you separate them with double arrows. And in this one, since I have the double bond there, I'll put a single bond there, the double bond going off in the other direction. Okay. And the other variation is with the double bond going down beneath the nitrogen. So I'm hoping that you had enough room to copy these on your paper somewhere, because what I would like you to do is label them resonance structures of nitrate. And again, I want to note that resonance structures are separated by that double arrow. Okay. So that's the end of my lesson. Teaching you how to handle polyatomic ions and what resonance structures are and how to draw them. So we are going to do some practice now, and I will help you with that. There are a few things you need to know before practicing. That there are never any double or triple bonds going to hydrogen or the halogens, your chlorine, fluorine, bromine, and iodine. It is common for oxygen to have a double bond, but it doesn't always. And then also, if you see a formula where you have something like C2H4 or N2H6, what you need to do is have those be like 2 central atoms where the atoms are next to each other like this and connected by a bond. And then you distribute the things that are attached to it around it. So here I'm distributing the hydrogen equally between the 2.